okay, and enter. So that number is going to be pushed onto the stack. Okay? So far, so good. Okay, so what's the next thing? An equal. So what does the equal mean? Pops the stack twice. So it's going to pop 8, it's going to pop 15. And then let's say B and A in this order. So this guy here is B, right? And this guy is A. And it's going to assign B to the variable pointed by A. Okay, so B is going to be assigned to A. Essentially, we're going to write 8, right, at the address 15 associated with the variable. Okay, so it's a simple write to a variable, an assignment to a variable. That's how you do it in mouse. Okay, so the next one is another string, right? So it's saying n is, and then you have an identifier, right? So we already know, so the stack is empty at this point, right? Because we did 2 pops, right? We already know what, when we see an identifier, it pushes the address of n, right? Which is 15, we're assuming it's 15, onto the stack. And then we see a dot. What does dot do? Pops the stack and uses its value as the address of a variable to be retrieved. The value of the variable is then pushed onto the stack. Sounds really complicated, but it's not. It's going to push the address. We'll look at the address, look at the value 8, and we'll push 8 onto the stack. Okay? All right? That's what dot does. And then we have an exclamation. So exclamation means what? Pops the stack, displaying the result on the standard output. So pops the stack 8 and will display 8 here on the output. And that's it for this program, right? We have $, that's the end of the program. So basically, it's a simple program that reads the value and displays the value using strings, right? Pretty basic. But the language, this language allows you to do if-else. So let's evaluate example 3. Example 3 reads a number and tells if it's odd or even. Let's see if it really does. All right, so the stack is initially empty. And you may think that, so it's based on the stack. This is very, just simple, right? But the Java virtual machine is also implemented based on a stack. Okay? So it's, of course, this language is much smaller, has much smaller scope and more rudimental, but it has the same principles of Java virtual machine implementation of Java, for example. So let's see this, example 3. First is an identifier, n. So basically, what does that mean when we see an identifier?
Pushes the address.
Pushes the address. Let's say that the address is 8. So this is the output. So let's push 8, right? No, that was the value. The address was 15. So 15, and this is the address for n. And then we have a string, same thing, right? And then question mark will input, let's say I enter, let's say 10, right? So I enter 10, the value is 10 is pushed. And then equal means what? 2 pops, right? And I'm going to write the value 10 at the address of n. Then we have n dots, right? N dots. So identifier. So we'll put 15 which is the address of n, and then dots. So dot will read the value. I already did all that, right? Question mark is the one that reads, right? So n dot. So n will push 15, right? And dot pops the stack and uses its value as the address of a value to be retrieved. Oh, okay. So we basically use it. So what does n dot means? N will push the address of n, and dot will pop and then push the value pointed by this address, which is 10. So basically, it will pop and then push 10, right? Which is the value pointed by variable n, right? That's what n dot is doing here. Then we have n dot again, okay? So we'll basically do the same thing, right? And we'll put 10 here. I wonder why does it have two n dots? And then it has 2, right? So 2 is just a number that is going to be pushed onto the stack, right? Because when you read a number, literal, pushes the literal onto the stack. That's the semantics. And then we have the division operator. So let's look at the semantics for the division operator. Pops the stack twice, right? Let's say B and A in this order. So this guy is B, this guy is A, right? We'll pop these guys, and we'll push A divided by B integer division. So it will do 10 divided by 2, integer division. No, it's not the forward slash, right? It's the backslash, right? Look at the table. The backslash is actually a mod operation, right? So it will pop and will divide 10 by 2, but it will push onto the stack the remain, right? The remain is 0. So 0, this is the state of the stack at this point, right? Then we have a bracket. Pops the stack, and so if you have a bracket, pops the stack and execute the statements inside the brackets. Only if the value is greater than 0, right? Is this value greater than 0? No, it's 0. Okay, so it will pop the stack, but it won't do anything, right? Because the value is not greater than 0. So this is how you do an if-else, okay? And what is saying there? We were to run what's inside the brackets. We will basically tell that the number is odd, right? But we know that this number is even. That's why this is not going to be executed. So it will basically just pop the stack, but it won't do anything. And then we have n dots. Remember what n dot does? It will push the value of n, which is 10, right? So it will push 10, and then it will push 1, okay? And then we have an addition, okay? So it will add 10 plus 1, and will push the result onto the stack, 11. Good. And then it will, I see a 2, it will push 2, okay, and will divide integer division 11 by 2. And that's 1, right? So 1 is going to be on the stack. And because this number is greater than 0, what's on inside the brackets, it will be executed, right? And what does it do? You have an exclamation, which is for output, right? Exclamation. Exclamation pops the stack, displaying the result on the standard output. Pop the stack. This guy, right? Pop the stacks, and it's gonna say, go right into there. So 10 is even, right? Exclamation. And then that's the end of the program, right? So as you can see, this program can tell if a number entered is odd or even, right? Are you guys able to write some mouse programs?
No, this loop stuff, I didn't get that. The next example.
Let's do you want to do example 4? Example 4 prints n times n for n in 1 to 10. Why don't you guys get a piece of paper and try to trace example 4 and see if you can figure it out. And then we will do it together. Let's go over here. Ready? Oh yeah,
That's way too future.
too future.
This big thing.
Oh, this big thing.
Oh, mostly industrial. Yes, indeed.
Yeah. Let's see which color.
You can just like steal someone's seat when you're talking. Who usually sits over?
People are normal. Personalities is there. Alex, you're-
This is a very.
How we doing? This.
I mean, open up.
Just open up what?
And stop sharing the screen.
I don't understand what.
I'm already working on this. Yeah. I couldn't too far.
So let's go through 2.
Split.
So we're not doing.
Okay, so we got an and a 1.
Party over here.
These and northwest. In equal 1. You have like this little address bar down here.
Hey, can you scroll and show me that definition?
Yeah, that one here. Huh? Scroll up here.
Should I keep going?
What is that?
Yeah, what is that?
It's just it is a identifier. That's an identifier.
Just address. Yeah, so
one gets pushed on stack now. Yeah. Okay. We got a friend. What do friends do? Wait, what do friends do? Executes the statements beside.
Yeah, so that's a. Yeah, it's a loop.
So this is
Actually, it's a for loop.
So
I'm
yeah.
kidding. I
It's
know.
definitely true. n dot. So we push that twice, right? So we push a 1 and a 1, and then we multiply them, and then we print and pop these to result, which is just gonna be 1.
So the answer is
Right.
So we printed
Yeah,
1.
it just gets a column. And,
So-
We need the equals, we popped it twice, right? So
This is our.
we only have one thing to pop.
So then we do 10 in.
It's a little together.
The carrot?
Yep. Statement, and that pops the stack and brings out of the loop if value returns 0.
Okay.
So effectively, it's our, like,
So
and it's not.
All of these are totals.
Wait.
pushes one.
While the top of the stack is not.
So push n.
Oh, okay, okay.
So it's iterating, it starts at 1.
So we push it in, we push it in,
Okay, so then.
we do our
the one
dot.
with more keys,
Uh,
and which says-
Wait, what does dot do again?
Pops the stack.
So we're just popping 1 again.
Please ever see that the minus.
So this
is
swaps these two values. Yeah, the dot doesn't pop it, the dot, basically like n dot.
Oh,
pushes the
10
value of
10
n
minus
to
1.
the stack.
Like,
Right.
the dot pops the stack and gives the variable at the top of the stack
Yeah.
to define the value at the address indicated by the variable.
Alright, we have this 10 first.
So it effectively replaces the top of the stack with a location, from like it replaces the
Right.
location of the top of the stack with a value.
You're right, the
Okay.
10 goes
So
on
does it
first,
go?
Yeah.
Yeah,
and then the memory address goes on, the dot pops the address. Puts n, which is 1.
Because n is an address, so every time we have n dot, you can see that as a pair for reading the value of n.
right. So we just got a 1 back again.
Yep.
Yeah.
So then we do 10 minus 1, essentially.
Effectively, yeah.
Might be the other way around, but I don't think it matters in this case.
No, I
Well,
think
subtraction
like,
matters, for sure.
Yeah, it's 10 minus 1.
I just did it. 10 minus 1. So now we have 9, so Karen does, what'd you say?
with top with exit out of the loop.
Put 14 and 1.
It is 0, okay, so because it's a 9.
Says that's not 0.
And do we store that 9 now, or do we? Okay.
So then we got the next,
So when it
And
calls
then we say
n,
in,
then it.
n dot, okay, so we're assigning n to whatever it is, plus 1. So we're gonna count up until that's 10, and then it's gonna be 10 minus 10, it's gonna be 0, and then it'll print. Okay, that is so confusing. I get it though.
the n dot that you normally.
Oh, sorry, I'm far ahead.
Yeah.
Like, I mean, they are.
I thought
so
one
things,
so
but
one
like
leaves
they
the stack,
effectively
it's
function
equal to
value,
right?
like, used to see.
Right.
So I'm sorry, I took this minus the parentheses, because the statement goes back on the stack. And
I
it's
get
all
this
blank
now.
statements.
I get this.
So-
Yeah, man, it's really good. Just download OneNote. And use it.
Find a pencil.
Then draw the rest of the owl.
They're really nice if you're in like a big crowd.
So just the copies are essential.
Especially if like if you want to go to meetings,
So then I'll
then
just
like
put
select
in
people for the
one.
meetings, or
Yes.
here goes, like, you're suddenly at a meeting and like, someone asks you a question and you're like, well about it, you can like be like, oh, just look over there and like scroll down, and be like, oh, it's this. Because someone else has the information.
You're using,
And so this is.
This is just gonna count to 10.
This should print out.
First time it'll print 1, second time
Second
it'll
time
print
it'll
2.
print.
which one you want? You want the
Third time
notification?
it'll print 9.
N dot.
Wait, say again?
So the second time, and the times and then it's.
It's counting down to 10, so it's, right, because it's starting with 10, and then first you
Oh, wait,
subtract
so-
1 from 10, and then you increase your value of n by 1 each time. So then, next time it's 10 minus 2, and it's
N
8.
will be 2 the next time, it's print 4.
Yeah,
Prints n.
You say.
Oh.
Then push the value of n,
Yeah.
pop both ends off, multiply together, push that.
So now it's gonna be 4, and then it's gonna be, wow, 9.
Opposite again.
So that,
It's gonna be squares.
that
Yeah,
10 though,
exactly.
at the beginning isn't always.
Well, I think that
I think
10
so.
is.
So the break condition counts down and counts up.
Yeah, so we don't touch that 10 and break, right?
But
Until
n
it's
is going
equal
up, but what it's printing isn't n, it's
Okay,
printing.
let's,
N
times
times
N.
n.
iteration
Yeah.
for the quotes.
In square.
It's
Okay, got it.
so 1, 2, 9.
So it'll do that until it prints 100.
Because whenever we have,
Yeah.
we just parse the whole thing.
Actually, will we actually print the 100? No, we'll print we'll print 81.
You basically add tab.
100, and then it sees the break.
Real quick then.
Oh, okay, because we're breaking at the end.
Then just turn it on
So
your
it's
stack.
10.
Right, if we put that
That's the
10
time.
or,
And
yeah, put the 10 dot place
14.
caret
If it was before the end of.
above, yeah,
Again,
then it will.
So
and then the dots, and there's one on top of it.
I don't like this language shortcut.
Yeah, the like
I mean,
whole.
it's intended to
happening
be-
right
Yeah, the
after
post-fix
the-
evaluation. I thought we were done with this after I saw it in computer science too, but
It's intended to be easy to compile.
So it's computer science
I
too.
think.
A
Yeah.
minus B onto the stack.
Yeah,
So
definitely.
it's 10 minus 1. So it's easier.
I mean,
You
there
pop
are
one,
some
10 off the
languages
stack.
that work
10 minus
like
1,
that, where
you
you would,
you
if you're
plot
mixing
95 from the
in a
stack.
subject to an object, you would say subject, object, and then verb.
Seems like a really
most
numbers.
I don't like that either.
You wouldn't do, well, maybe you would do
No,
object, subject.
Not
verb,
English.
They're good for a sideways nine?
Is,
It is.
Okay.
subject, verb,
Right,
object,
right.
and then the most, and
Barely, but.
Return to
so like,
zero.
some people say that like,
That's our end of our while
it's,
statement.
it's like there's 2 different ways to do it. So there's subject verb object, there's verb, like subject object,
Okay, so
there's
pop stack and breaks
verb
out of
object
a loop
subject, and
if
then
the
there's
value returned is 0.
object.
So shouldn't
verb,
everything be popped off the
subject,
stack then?
because the one that's
Uh,
no
Only
one
this.
and some people say.
So it's a process stack, it
It's only
only pops one stack. Okay, man, that's confusing.
I know, right?
Talking about, like, one,
So
you know,
9 just
use it. If you're about number of
Which is kind of weird.
Okay, so we have a
it's the same way English does it by default, with English and Mandarin and like
yeah.
every other
so
Indo-European language do.
So, and
Okay, let's try. it. You a linguist?
No.
No, they
Full of random facts.
Fact brain.
Said it.
Okay, so
If
this
you
is
ever watch
the
FNA,
stack.
like they don't follow.
We have n. N puts the,
Thanks for carrying the team, buddy.
puts the address of n, right, onto the stack, all right? And then 1. Pushes 1, right? Equal. Pops the stack twice, B and A, assigning B to the variable pointed by A. So basically, we're going to assign 1, right, to the right one at that spot, right? At that address. It's basically how you do an assignment in mouse. First, you push the variable, the address, and then the value, the right side of the assignment, and then you interpret the assignment statement. Then we have parentheses. So parentheses mean what? Execute the statements inside the parentheses continuously until a break statement is found. A break statement is the
Circumflex.
Caret.
Circumflex.
Circumflex. I know that. Circumflex. Caret.
I like circumflex.
That's whatever that is. Yeah. So let's start by interpreting. We have n, so it pushes 15. Then we have a dot, which pops and pushes the value 1, which is the value of n. And then again, 15, right? And then pops, put the value 1. Multiplication, well, we already know it's going to multiply them, right? And it's going to push the result, which is 1, back to the stack. And then exclamation. The exclamation will pop the stack and display the value. So pop, display 1 there, and a space, very important space. All right, 10. pushes 10, and then pushes, well, when we see n and dot, I'm just gonna put the value of n, right? Because we know that's what's gonna happen. But those are two stack operations. And then we have subtraction. So 9, right? This is the state of the stack. And the break. When does it break? Pops the stack and breaks out of the loop if the value return is 0. But the value return is not 0, so we're not going to break, right? And then it's going to do n. So it's going to push the address of 15, the address of n, and then n dot. N dot means push the value of n. Then push 1, addition 2, right? And then the assignment, right? So the assignment is going to put 2 here. So we did all that to increment n by 1. Right? A lot of operations.
It's
And
not
we're going to
increment.
the next iteration of the, yeah.
Is that an increment though? Because next time won't it be 2 plus 2?
No, it adds by 1.
Oh, is it just 1?
Yeah, I'm sure it adds by 1. So let's do one more iteration. I'm not going to do 10. Just do one more. And then we skip and see how it breaks the loop. So next time, the stack is empty when it starts the loop. It will push the value 2 n dots, push it again. Okay. All right. Okay, because it prints n times n, right? Okay, so n times n, 2 times 2 is 4. So 4 here, after the multiplication, exclamation, 4 in a space, right? And then, so when we do the exclamation, the value is popped out. So now we have 10, and the value 2. Then there subtract 8. 8 is not 0. So we're going to keep doing one more iteration. Doesn't break the loop. All right, so now we have, this is popped out. We push the address, right? So 15, address of n, and then we push 2 twice. No, we push 2 and then we push 1, right? Push 2 and then we push 1. We add them both, 3. And then we assign 3 to n. So 3 is assigned, and we pop everything out, and that's the end of the second iteration. Okay? So eventually, as you can see, the n eventually, so we incrementing n by 1s, right? Eventually, n is going to be 10. Okay, so let's assume that n is 10. Okay, so let's skip a few steps. So at least we see the break. Okay, so we have 9 times 9. Right, so we're at this point that n is 10. We're starting a new iteration of the loop. So we do n point, 10. N point again, 10. And we multiply them. So 100. 100 is going to be here. And then we pop this out and we print 100 in a space. And then we push 10. We push n value, right? 10. We subtract them. Oh, look at that, 0. Okay, and because 0 and the circumflex, so that breaks the loop and the program ends. Okay, so it's a simple language, but you can do things like loops like that, and you can even do nested loops. Right, the next example, I'm not going to do it, but we're going to run it actually, and does a nested loop. The interpreter can deal with nested loops, many levels as you want. Okay. How do you like mouse?
I don't.
You're going to spend the whole 3210 from now on just using mouse.
So.
Have to love it. Okay. That's your programming assignment. Okay. The goal of the programming assignment is to do the lexical analyzer and the syntax analyzer. The mouse interpreter is given to you. I can try to open the solution, but I have to be careful not to show any code. Let me try to open here just to run some of the examples using the interpreter. So let me give you just a quick demonstration of, after you're done, what should you expect? Let's see here. Okay. So let me share my screen. Okay. So this is the interpreter. Okay, so mouse interpreter. And if you're curious, you can read the interpreter, but you're not required to do anything in this mouse interpreter code. As you can see, so the key here for the mouse interpreter to work, your parse tree should have the exact format. Otherwise, it won't run because it expects the node to be labeled accordingly. Okay? If you label differently, the mouse interpreter will not be able to run your code. Okay, so make sure you read the instructions have examples of how the parse trees should look like. You have to follow the exact labels, use the same name for the labels and everything. Otherwise, you won't be able to run the programs. I'm gonna run some here. See, let's start with example. What was that example? It was 4. I'm gonna do the third one. It was the if else. Okay, so it's running here. Say 10 is even. And 1 is odd. So if else worked, let's try example 4. The one with the loop. Okay, so it worked. example 5 has a nested loop. 2, 10, that, okay? And I think the most complex one was example 12. So count now, let's say 100. No, not that. 100. Okay, so doing a basic countdown, but it keeps going. And another countdown until I hit 0. That's when it ends. Okay? So it has an if, else, and a loop to combine those things. So be creative. You're expected to write a mouse program at the end too. So, and the assignment has many opportunities for bonus points. Okay. Those are the examples of the sparse trees. Let's take a look at the bonus points. So what should you submit? You need to zip the token, Scala source, lexical analyzer, and the syntax analyzer. I don't need the interpreter. Unless you make to gain the bonus points, if you probably, for some bonus points, you have to change the interpreter. There are some bonus points that require you to change the interpreter. So of course you need to submit the interpreter as well. Example 11 is your own program written in mouse. Why is it 11? Oh, there is one 11. There was one of the examples one of the students sent the last semester, I guess, checking you can buy alcohol or not. So let's do this. You're gonna have, since I already given you 11 and 12, you have to change. You have to submit example 13. Okay, so you have to come up with something different. That's example 13. Bonus opportunities. 5 points. This is very easy to do. Easy 5 points. Implement commenting. Right? So according to the creators of mouse, single quotes, anything written after a single quote should be ignored. So if you add that feature in your lexical, maybe the lexical analyzer should be changed to ignore comments. That's an easy 5 points. If you add that, I will check that. Another thing that you can do that will give you 10 extra points is to implement functions. Okay, support for functions using macro definitions. You have to look online for the correct syntax and semantics for macros in mouse. There's a link for, I think, in the beginning of the instructions that points to the more information about extensions of mouse. The original version of mouse had the possibility for only 26 integer variables because it used the letters of the alphabet. Our implementation is slightly better because it does lowercase letter and uppercase letter. So to get 10 more points, if you remove limitations on how you define variables and doing like dynamic memory allocation, you can get 10 more points. So you can go up to 25 points in this assignment. Pretty much, you just don't need to do anything, right? 25 points extra in an assignment. Well, I think it's a great opportunity for learning other things, but you're not required to do the bonus points. If you want, just do the 10 basic points, okay? Just a note, the bonus points do not overflow beyond programming assignment. So don't expect the 25 points if you got 100 in all assignments. you're still gonna get 25 more, but only in programming assignment section. It doesn't overflow. Oh, super, move that to final exam. I can't do that, okay?
25 points for homework. So I'm gonna do another assignment.
Can you imagine that? Homework is a different scale.
What if we get all the bonus points all semester? Then can we get like another 5 toward our exam?
Or move to database system. I have a student that asked that. Professor, can you move 25 for next semester in database? Totally uncool. Okay, any questions about the assignment?
45 points in the class.
Okay, so take a look during the weekend. You have like 2 weeks to finish, start earlier, do the token, the lexicon analyzer. That's what I would do. This weekend, I would focus on the lexicon analyzer, the token. Once this is done, do the top-down parser that we discussed. Should be easy, all right? And if you have time, try to get bonus. All right, so today, I want to talk about another type of parser. And today we're going to finish this part of the course that talks about, well, at least we're still going to talk about semantic analysis, but pretty much will be done. And then after 1 week, I think we're going to switch to functional programming. So let's take a look at lesson 8. That talks about the bottom-up parser. Okay, it's a different type of parser. As the name suggests, it builds the parse tree bottom-up instead of top-down, as we have been doing. The type of parser that we're going to talk about is based on the shift-reduce algorithm. So it's uses 2 operations that we're going to discuss today, named shift and reduce. Okay. So basically, the shift operation happens when the parser decides to read a token and consume a token and create nodes. Okay. The reduce is moving up in the parse tree. It condenses nodes into a variable. So that's the reduce, right? It collapses nodes into a common parent node and moving up in the parse tree. So the shift operation adds new trees to the list of 3. So during the parsing process, the parser maintains a list or a collection of trees, right? And those trees are not connected. And at some point, it will collapse those 3 nodes into a common parent, as I mentioned. So the shift adds trees to this collection of trees that are currently being evaluated. And the reduce condenses 1 or more of the trees currently being evaluated into a common ancestor node, essentially building the parse tree up. The goal is to find the specific combination of the inputs that must be rewritten using one of the grammar's productions. So that's the main goal of the bottom-up parser, is try to find combinations that can be rewritten using one of the productions. To find this combination, the algorithms, they based on what they call the handle. Let's take a look at this example. Consider that at some point the input is E plus T times IT. Okay, so this is the state of your evaluation. At this point, you know you have a expression, a variable. You have a token, addition, you have the T, you have multiplication, you have ID. So how can you, how do you decide which production, and the production in the bottom up, you apply in the reverse, right? Because in the top down, we always figure it out based on a variable. How can we replace that variable by the production, right? The right side of the production. In the bottom up is the reverse. We have some symbols, and we need to figure out which production was used to create those symbols. It's bottom up, it's the reverse process. So what are the, based on this grammar here on the right side, in this state, the possible handles, what are the handles? A combination of variables and terminals that you're seeing in the current state of the evaluation. And you're going to figure out which part of the state of your evaluation should you use. For example, there is 3 possibilities here, right, for handles. One is E plus T. How do you know E plus T is a handle? Because I know that there's this production here that has E plus T on the right side. So technically, I can reduce E plus T to an E, right? That's the reverse process. So this is a possible handle. Is only plus T, do you think that's a possible handle? No, because there's no plus T only on the right side, right? T only is a handle. Why is that? Because there is a production that goes from E to T, so I can go from T to E in reverse. Can you see what our handle is?
Oh, we just look at whatever's on the right and see if that
Yes,
expression
right?
is there.
For example, is T times ID a handle?
Wait, wasn't that the same as T times F?
T times ID. No, this is T times F. That's not T times ID,
Oh, yeah, that's a terminal.
right?
No.
So it's not a handle. Just ID is a handle. Yes, right? I can turn this ID into a factor, right? So there are 3 possible handles. Can you see any other handle here? Only E is not a handle, right? E plus is not. Can't see any other combination, right? Asterisk ID, no, it's not enough. You need the T. T times ID, you don't see it here. I don't see any other possible handle. Those are the only possible. Yeah.
So this grammar would have 6 possible handles?
Yeah, but you have to look at the current state of your process. This is the state at some point of the process. This is what you had identified at this point. So the handle is not based on just the grammar. It uses the grammar, but it's based on the current state of the process. Okay? And we're going to do this step by step. I'm just showing that finding the handle is trivial. Like you can easily implement a program that is able to identify all possible handles, right? Just need to do combinations of strings and look at the right-hand side of each production. The problem is not all handles lead to the right path, okay? That's the key, okay? Let's try this first handle, okay? Let's say, okay, you have basically, because you have 3 handles in this example, you have 3 possibilities to going up, but not all possibilities will lead you to like the start symbol. The goal is to reach the start symbol after processing the whole input. So let's see the first handle. So we're gonna replace, okay, E plus T, we're gonna replace by an E, okay? So E plus T, so what's gonna be our input after we replace E plus T by E? E plus T will be replaced by an E, so we have E times ID.
So
Can we do anything with E times ID? What are the possible handles when you have E times ID? Do we have more than one handle for E times ID or just one?
just one, we have to go to
Just one, right?
times that.
The only thing we can do in this situation here is turn ID into F, right? ID is the only handle. So ID can turn into F. But E times ID or times ID, those are not valid productions in reverse. So the only possibility is turn ID into F. Let's do that. That's the only possibility. So now I have E times F. Is there any handle we can use here? Turn F into T. So F is the only handle here. Okay, I can turn F into T. So let's do that. That's the only possibility. Do you agree that's the only handle we have? Yep. There's no other. There's no production like multiplication F or E times F or E times. We don't have that. The only possibility is turn F into a T. And that's the handle we're going to use. So we're going to turn F into a T. So now we have E times T. What should we do now? Well, I assume it's a dead end, but we can still do something, right? We can turn T into E, right? But once we have, so I'm going to use T into E, okay? And then we're going to have E times E. Can we do anything about E times E? There's no way to go. There's no handle, right? You can't move up in the tree, right? So that's a dead end. Do you agree it's a dead end? Of course, after replacing T, still can go T to E. But then once you have E times E, there's no way moving up. So that's a dead end. So that wasn't a good choice. So let's try the other handle. Okay, so we decided to use T as the handle. So we're going to replace T, right, by E. Okay, so when we do that, right, we have, this is what we have at this point. E plus, instead of T, now we have E, right? E plus E times ID. Do we have any handle that we can use? The only one you can use is ID turning to F, right? Do you see any other?
How'd you get E plus E times ID from T?
We replace T, right? T is the handle. So we're gonna use T because E can go to T. We're doing backwards. T going to E. We're moving up. So we replace T by E.
Oh.
So we're just trying all possibilities of something on the right turning into something on the left.
Yeah. So the only possibility here is ID going to F. Do you guys agree? Okay. So we're gonna do that. E plus E times F. Again, the only possibility we have, hopefully you guys agree, is going F to T. So this is what we have now. E plus E times, well, we turn the F into a T. That's what we have. Can we do anything here? The only thing we can do is turn T into an E, right? There's nothing else we can do. We have E plus T, but we don't have E times T. Okay, so the only possibility is turning that T into an E. That's a dead end. We can't move up when we reach this state. So that wasn't a good choice. Okay, so of course, the choice we should have done was the ID. Use ID as the handle. That's the only possibility for this grammar. Okay, because ID leads to E plus T, right? And once we got E plus T, we can go to E, which is the start symbol. So we reached the start symbol, right? Not so fast, Professor Volta. E plus T, we turn ID into F, right? Then we did, I assume nice, but I should have done all the work here. So what's the other possible handle? So there are actually two possible handles here, right? So we should evaluate the two possibilities, right? So let's use E plus T as one of the handles. And the other one is doing T times F. So there are two handles here, right? So let's try the first one. So if I use the first handle, E plus T, I'm going to turn it into an E, right? I'm going to have E times F. And then what? What's the only possibility there? F, right? F into T, right? So the only way to continue is turn F into T. E times T, can I move forward? I can't, that's a dead end. So this wasn't good, dead end. Let's try the other one. So I'm going to turn T times F, right? T times F, I'm going to turn into T. So I end up with E plus T. Ah, now it's nice. E plus T. Well, I can still do stupid things here because I can turn the T, right, into an E, right? But if I do that, that's not a good choice because E plus E is a dead end too. The only right choice was to turn now E plus T into E, right? That's the only way to go up, okay?
So we reduce this until we get to the start symbol.
Yeah, so that's a good question. So you guys can see that there are different possibilities, right? We just need to find one, right? But the thing is not that simple because if the code is correct, okay, we need to find one. But you can't have like a code that is synthetically wrong that one of the possibilities lead to the start symbol. That will also be wrong, right? So there's some theory behind on how you make sure that when we reach the start symbol, the code is actually synthetically correct. We're not going to go into details about the theory behind of the shift-reduce algorithm, but again, the shift-reduce operations, shift means reading the next token symbol from the input onto the parser stack. So the implementation uses a stack to control the symbols that are being evaluated, right? Because these symbols here, E plus T times the state of the current evaluation of symbols, including tokens and variables, has to be placed in some data structure. Data structure we're going to use is a stack because the stack preserves the order, and we're going to, it's an efficient way to deal with these symbols and put them nicely in a data structure. The reduce will rewrite tokens. So the reduce operation will remove symbols from the stack and will push other symbols onto the stack. The shift will basically just push symbols. So this is how the so-called shift reduce parsers work. One type of shift reduce parser is called the LR parser, developed by Donna Knuth in 1965. To define whether you're going to do a shift or reduce operation, the algorithm uses a table. And what we're going to do, we're going to use a tool that generates the table for us. I'm going to talk about this tool, but this is the output on the right side here. You see LR table. That's the output of the table of the online tool that you guys are going to use. Basically, this table will define the actions we should take at each step of the evaluation process. As you can see, you have, it's a state machine, basically, okay? Because depending on where you are during the evaluation process, which state you are, and depending on the input you're reading, the parser will behave differently. So that's basically a state machine, and that it's going to be one of the inputs of your parser. You're going to use a table to basically a state machine to control how your parser will behave. So you have the states and you have the tokens, right? And you have the actions. So as you can see, for example, S5 means shift. So shift will consume the input and will move to the state 5. Shift 6 will process the input, the multiplication, and will move to state 6. So the machine at each operation will decide, based on the table, whether it should do a shift or a reduce operation. Reduce operation is a little bit more complex because it needs to, what is reduce to, for example? It's this to here is not a, it's not a state. Is going to be used to decide the which let me check here. Oh, the reduce. Let me oh, okay, I remember. The reduce actually show number 2. It's this number 2, right? You have reduce 2, reduce 4, refers to the production that should be used to condense the trees. Okay, so we're gonna see that in a step-by-step example. We're gonna use this grammar. And let's start. So first of all, assume that this table is correct. You have the grammar. All the values, productions are numbered 0 to 5. Those numbers are important. And this is the state of the stack, and you have the input. Okay, so this is the program you want to evaluate. And this program is the statement, right? This expression is synthetically correct. X plus Y times Z. That's synthetically correct. The dollar means that's the end of the input. There's nothing else to read. Okay. So let's start. The initial state is 0. That's how the algorithm how it initialized the stack. And let's assume that the top of the stack is on the right side. Okay, so we push on this side, and we also pop on this side. Always on the right side. Okay. Okay, you guys ready? So let's do the shift reduce algorithm step by step to evaluate this expression here. Okay, so I'm reading an X. Okay, we know that an X is an identifier. So, and we know that the state, current state is 0. So this is how the algorithm looks at where to go. State is 0 and is reading an identifier. So this is the operation that should be performed. Okay, so state is 0. That's the state of current state, always at the top of the stack. And the token that is being given is an identifier token. So we're gonna do a shift 4. So shift 4 means what? Push the token, okay? And move to state 4. So let's see this happening. Okay? We're also gonna be creating 3 nodes. Remember, we're doing this bottom up, okay? So we're gonna get the label of the input. We're gonna create a node with the label, okay? And we're gonna push 2 symbols onto the stack. The first one is the identifier, right? That we just read in the new state. Okay, so we're gonna push twice because one is the symbol, the other is the state. Okay, so that's the state, the current state of the parser. The parser read one symbol from the input, created a node with the label X. We're gonna move this up, and the state of the parser is state 4. Okay. So shift operation, it's easy, right? You just do, every time you do a shift operation, that's what you do. You consume the input, create a node with the label, and push onto the stack, making sure you move to the state showed in the operation. Let's see what's coming next. Okay, so next we're reading an addition. Okay, so an addition, state 4, the action is reduce 5. So we're going to do a first reduce. What does it mean, reduce 5? 5 refers to the production. Okay, so what's the production number 5? This one here. So basically, this reduction means I want to change the ID into an F. Okay, so this is what we're going to do. We're going to create an F, and we're going to connect one tree, because we're only seeing one symbol on the right side. So we're just condensing one node. That's why we only connected one node to this new node we created. So we moved up with the F symbol. We pop the stack. We push F, which is the variable now, F. And we need to figure out what's the state. Okay? So that's when you use the go-to call. Okay? So the go-to, you need to look at 0 and F, right? 0 is the state. F, where should you go? So 0, F, you should go to 3. Okay, 0, F, you go to 3. Okay. So let's read the next. And remember, the reduce operation does not consume the input. So the input is still addition. So the next operation, we're seeing an addition, right? So an addition token, state 3. So 3 in addition, it means reduce 4. Reduce 4, this is the fourth operation. We need to go from F to T. Okay? And we're just going to condense one tree. This is all considered one tree now. Okay? So we're going to do the reduce operation. We create the T, right? We collapse one tree, which is this tree that had F and X. Connect to T. We top, and we push the T, and we need to figure out where to go. So 0 T, we should go state 2. Okay? So it's a very detailed process that the algorithm follows based on the table. Okay? It's basically a code that the intelligence of the code, we can say that the code is smart, is given by the table. The table has all the transactions that the algorithm should follow. Okay? It seems complicated, but the algorithm itself is going to be really short because all the logic is embedded in the table. And we can generate the table automatically. I'm going to show you how to do it. Okay, so now addition. State is 2, right? Addition, so we need to reduce 2, which is turn t into e. You see that we're moving up, right? And e and 0, we should go to state 1. That's the new state now, okay? We still haven't consumed the addition. So let's see. State is 1, right? In addition, we should do a shift 5 now. Okay, so we're finally going to consume the addition. Okay, so we pushed 5 and 5, addition and 5, so the state now is 5, and a new tree was created. So now we have 2 trees. We have this big one here. We have this new one with the label plus. And the plus was consumed. So now we're going to read an identifier. An identifier, 5 identifier, we should do shift 4. So shift 4, we're going to consume the y, and we're going to create a new node with the identifier. Okay, I put it in the bottom because I know we're going to reduce this up to e. So this is the state of the stack. The new state now is 4. And we consume the identifier. And now we see multiplication. So multiplication in 4, right? Multiplication in 4, we should do reduce 5. Reduce 5 is turn that identifier into an f. So we're going to move up here. Okay? And f and 5, we should move to state 3. That's the new state. We didn't consume the multiplication because we did a reduce. Let's do again. The next step, we are at state 3, reading multiplication. So that's reduce 4. We need to turn that f into a t, as we were expecting. Moving up, now we have three trees here. T and 5, we should go to state 7. Okay, we still haven't consumed the multiplication because we're still going to do state 7 input multiplication. We should do shift 6. Shift 6. Shift 6. This right? Oh, shift, not reduce. Okay, shift 6. Basically, we're just going to consume the multiplication and we're going to push and move to state 6. Okay, so we consume the multiplication, move to state 6. Now we have 4 trees actually. Can you guys see that we're moving up and creating bottom up the tree? So now we have an identifier, state 6 identifier, so that's shift 4. Okay, so shift 4, we're going to read this identifier, create a node for z. Okay, look at that, z and 4. We state 4, and we have 1, 2, 3, 4, 5 trees. Okay. Okay, now we're reading dollar. So we were able to read the whole input, but we still need to see if all these trees will eventually collapse to S. So we need to do reduce 5, turn the identifier into F. So this, it's always from right to left. So because we're doing the reverse. So Z has to be turned into F, and we need to pop these guys out and replace with an F. F and 6. Move to state 8. State 8 in dollar, we should do reduce 3, which is this guy. So T times F, you see, T times F should be condensed into T. That's what we're doing now. T and state 5 and T, we should go to state 7. And when we are at state 7 and we read a dollar, we should do reduce 1. Reduce 1 is E plus T into E. So we're going to condense these guys into an E. Okay. And now we have, which state should we go? E and 0, state 1. Okay. And 1 and dollar, ACC. ACC means what? accept. Correct?
I don't like it.
I don't like it. You don't like it? No. Just repeating what you said.
Except for the whole creating that table thing.
Yeah, the table, but she said, they're getting sure, you got
You
something to
said you
make
didn't like it. I like it.
No, I like it.
No, you said you didn't like it. No, you said you liked it.
Oh, no, I like it. I like it.
I thought you said.
As
that
long as you
you
give
liked
us something to generate that table.
Yeah. So, so how to generate the table? So open the activity 8. So the first step is to
Activity 8 or activity 9, Professor?
activity 9.
Thank you.
Activity 9, yeah. Thank you. So unfortunately, the tool does not accept EBNF. Okay? And that's one of my goals on my to-do list is to create a tool, an online tool like this one, but that would accept EBNF natively. Because that would be great. I'll just pick the EBNF grammar and use that. But it's not a big deal. For smaller grammars, you just need to turn into this format. It requires the arrow instead of the equal. Okay, and you of course you can't use EBNF repetition and those special symbols. Epsilon should be replaced by an empty string. This grammar doesn't have epsilon. One good thing about bottom-up parser is that you don't have to worry about left recursive productions. So it just accepts. You see these productions here are left recursive, and you can just plug in and it should work. Okay. From my experience, the tool doesn't like having the start symbol on the right side of any production. That's why we have the start going to expression and then expression going to something else. It's just a hex so the tool works. I noticed that in a few examples. I can't just have expression as the start symbol also appear on the right side. The tool doesn't like that. So let's just click on the link. Okay, open link. 30 students open at the same time. This website is. Okay, so you can just replace, remove the extra spaces. Okay, and when you're ready, you see, use the empty blank here as epsilon. So you can hit, and this is the steps of the generation process. We're only interested in the actual table, and that's the table, okay? So this table has 0 to 16, 17 states. Let's see if it matches the one that, yeah, so it's exactly the same one that I generated earlier. Okay, and you can actually test and see the parse tree here, for example. Now, of course, you're not going to use, for identifiers, you should use ID. No, you have to use, yeah, ID, right? Because I'm using, no, I'm using identifier, so I have to use the actual whole word. So identifier plus identifier. Maybe I'm going to put, this grammar has parentheses, so I'm going to put the first two using parentheses. All right, and I'm going to parse. Look at that. This is the parse tree, and we were able to ACC, so that was a good. And look at the parse tree identifier going to factor, to term, to expression. I don't know how he did that. That's pretty cool. Using HTML. That's pretty cool. And going up, okay, so you can see the structure of the tree. Let's put a arrow here. So I remove the parentheses. I'm going to try to parse that, and it fails. Okay. So how does the algorithm know when it fails? If at some point reaches one of these blanks, so there's no way where to go. So that's a like a syntax error. For example, if I'm at state 11, I should be expecting addition and subtraction only, or maybe a closing parenthesis. If I reach a situation where I'm reading a different symbol other than those, that's the syntax error will be expecting addition, subtraction, or closing parenthesis. That will be the syntax error.
Did you just copy the grammar from 39?
Yeah, but not the EBNF. I copied this one here that you have to change you have to use the format using the arrows. If I use equal, it doesn't work. People think that equal is a symbol. It just doesn't work. Okay? For example, let's try some other grammar to generate something different. Let's get some of the past grammars we use just to we did. How about the homework? Homework 3. Homework 3 grammar. Let's try to code that in the format that the tool understands. Again, you have to do a start. So this thing is optional. And extend is also optional. It can be more than one. I have to do all the combinations, right? Because you can only have one production per line, so that's another limitation. Now we have to combine adding the extends, right? Extends and implements. Oh my gosh. EBNF is so much better. This one should have another possibility of having extends. Right? And now we have to create one for each with the implements, right? Explosion of productions. Getting tired. Okay, identifiers we can leave as identifier. Extends is we're using the same name for the variable in the token. That's not good, right? So let's use for the variable, put something different. Okay. Otherwise, it will create a confusion. The same for implements.
Okay, why are we doing that?
Because the keyword is also implements, variable is also named implements. We don't need letter, we don't need digit. Type is an identifier. Type list is type or more than one type. And I think we're not doing implements because we can have a list of type list. Okay. So it can be one type or type more, and type more, the comma, type more, comma, type more, right? Or epsilon. I don't know if this is gonna work. Okay, so that's basically the work you have to do to adapt. Make sure your grammar is in the format that the tool expects. Let's try that. At least one type or many types, right? This is we'll do the repetition. Let's see. It did generate some. How many states? Just 23? It seems so sparse. Shall we try to parse something here? Let's try something very basic like class identifier. Brackets, or braces, right? So parse that. It did work. Do we dare put in public? Public. It worked. We missed the brace. 0. Good. Let's try extends. Public class identifier extends identifier. That should pass. It didn't pass. Some problem here?
How do you track down what's wrong?
Class identifier
It needs an
extends
underscore for extends.
underscore V for extends.
Right at the end of extends, it's looking for an underscore.
Oh, here, right?
Uh-huh.
Forgot the V here. Maybe that's what.
I thought you did that on purpose.
It'll work now. Okay. How about implements? Implements identifier. Just one for now. Didn't work. Implements identifier. Implements. Here should be implements V. Right? All right, let's try again.
I think you're missing another V on line 7.
Implements V.
Into line 7.
Okay. Good. Nice. Okay, let's try 2 implements. Oops, identifier. Didn't like that. Oh, maybe because I didn't put a space for the comma. So let's try again. Oh, it was the space. Okay, so that demonstrates that it works, right? You just need to be patient and use the same formats. But the good news is once you have the stable has changed 33 states. the algorithm just uses the table as the input, and it will work. So it's easy to prototype and test different parts. You don't have to change your code. The code is the same. The only thing you change is the input table. So that's a plus for those type of parsers, right? And the implementation is very efficient, right? You don't have all these function calls, right? It's basically just a state machine, and that can be implemented really efficiently, right? Well, we're not going to go into details how the table is generated. That's out of the scope. It's more theory of computation. Maybe you can ask Dr. Paul. Dr. Paul, I want to know how the LR table is generated. Okay, you guys enjoy your weekend. And next time we just gonna see how the algorithm works in more detail. Okay. So this next week, exceptionally, I'm not gonna assign a homework.
Yes.
So you guys focus on starting the programming assignment, okay?
I'll team it up with you. Yeah.
Good luck. Professor,
I guess.
wish me luck at the half on Saturday. Just like, I have a hat on Saturday.
Oh, is this Saturday?
Yeah, it's my first road race.
I'm seriously thinking of getting that surface.
See.
Yeah, okay. Yeah, if you want to bring it Monday. I got you.
I'll be here tomorrow too. I can be back, but I'm nervous for like a month.
Okay, I'm here for an LA
Point
class,
is
so
like
yeah.
ideally to like reassure.
Just lounge yelling at each other about the project.
Listening, I'm
What
out.
time?
Oh, you're
right.
So this project.
Okay. Yeah, I'll look for an email from the.
Okay. I haven't done any
Just
road.
say going in. I'll hit you up then, yeah.
Oh, is it this
This
week?
weekend.
Friday.
Yeah, that's what I have time for this shit.
See how the road race are doing.
Well, it's up to you, I mean,
So I've done
like,
like.
the first part,
Yeah.
so when we started working on the lexical analyzer.
I might be picking you up.
But we didn't work on it that long.
So it's on your body.
Mo was there.
So, yeah.
So I can work on other stuff. Yeah. Courtesy of I don't think it's gonna take, I think I might be done with that tomorrow. The parser takes more time. I think.
The weather is nice.
Algorithms take more.
Sounds good.
Yeah. Certainly not.
But I did 8 hours.
Tomorrow,
Especially like trends down.
So I'll be here at 8 AM. Finish
Everything up or down?
Going up.
I don't know how
Not a good idea.
I did just a 5-day this week at high school.
Yeah.
You know what?
Very good. Yes.
Yeah.
It was on my, it was underneath my phone. My laptop, so I slid upstairs and fell.
And then a couple days ago, and she did 43:30.
Oh, wow.
It's like she's barely been training and she was disappointed, like it's 2 minutes faster than I've ever run in my entire life. You bitch.
Oh, good luck.
Yeah, no, thank you. I
Let me
will,
know how
I will
you
tell
go.
you how it goes. So I'm hoping like sub 2 hours, that's all I want.
Oh, that'll be great.
Would you be fine for the programming project if we use that tool to make like that state machine and then wrote the SLR type parser?
Oh, do you want to use that algorithm for the
Yeah.
assignment? Yeah, you can
So
do that.
it's probably gonna take the same amount of time either way, but that sounds like a more interesting way to spend the time.
Yeah, and I will be sharing the code. So it's basically it's just generate the table, and of course there's the lexical part, but the syntax analysis is that the one that takes more time. Yeah, if you want to try that.
Write the syntax analyzer. But
Yeah.
I mean, like I said, that'll take more time, but it's probably more interesting time than figuring that out than just writing the recursive descent.
Yeah, yeah, and the recursive descent is, after you figure it out, it's kind of boring, right?
Yeah, that's
At least this one you have kind of a challenge to.
Yeah, it'll be less code.